Today, I feel really humbled and privileged to talk to Dr. Bernard Lee. He doesn't like me to call him Dr. Bernard Lee, so I will call him Bernard. He's the Director of Technology and Innovation at SENKO Advanced Components. Bernard has over 15 years of global experience in the telecom and data communications industry. His trajectory includes being the head of photonics and network research and head of innovation and communications at Telecom Malaysia. He is also an expert at the IEC, International Electrotechnical Commission, among other important roles. Bernard recently wrote an article called From a Dog's Dinner to a Three-Course Meal, more on that later. He describes the evolution of data center architecture and how, thanks to the best standardization practices, the industry has really significantly improved the architecture and infrastructure to optimize data transmission and network reliability. So Bernard, welcome to Todo Fibra Óptica. And before we get started, I would like to invite you to tell us a little bit about yourself, where you live, your trajectory, and your current role at SENKO and involvement with other standard bodies, please.
Thank you, Jose, and thank you for having me on the show. It's really a privilege, and meeting you in person is really an eye-opener. Well, a bit about myself. I actually live in Malaysia. I'm Malaysian. I've lived here for all my life, I would say. But I did my degree and my postgraduate in the UK. And later on, as we talk about and why the title of the article came along. In SENKO, I joined SENKO in 2011. At that point, I was the director for R&D. And in the same time, what I've done is I travel around the world and I try to help the clients for SENKO on their design and their solutions. And right now, I'm the director of technology innovation. The title is a bit vague, but it really means that my responsibility includes looking into standard bodies. What are the current technologies so that we make sure we are giving the customers the latest standard and not something outdated. And of course, innovation. And that's something that SENKO prides in. We try to make our product not the vanilla, not just a plain vanilla flavor, but we try to give innovation and see how this innovation could help make the lives of our customers easier and better. And I've been doing this for the last several years. It's been exciting, and I get to travel the world as well and meet very interesting people and experts.
Great, thank you. And I know firsthand that you're really well known in the industry. You know, some people that I know very well, they know you and they respect you very well. So once again, thank you. And so diving into your article, and I think we'll share some images as we discuss it, because I think they describe properly exactly what you mean. Let me share my screen. But first, if you could, before we start with that, actually, tell us a little bit about the challenges briefly of what it takes to come up with these guidelines and standards as you have to talk with other key players in the industry. How is the process? How tedious? How long? What does it take to really be able to come up with solutions that benefit the whole rather than the individual?
Understood. So if you look into the background of what a standard is, if you look in most of our design work and everything, the pinnacle of all design work has to be laws, and it's not the guidelines, but it's actually the acts in different countries. We first have to look into the countries, what their requirements are, and these are something that we cannot change. Coming down from that, our clients and customers always have different policies in design. Some customers require eco-friendly, some customers require certain products to be made from certain materials or lead-free. And then these are something that we also need to comply as determined by the customer and the government of the country. Standards is the bare minimum, which means that it is not enforced by law, but it is an industry consensus. So working standards, the greatest challenge is to get the consensus of everybody, saying that this is a standard, although it's not required by law, it is the industry's agreement that this will be the bare minimum we will need to impose. And that is the first step. Standards can never be adopted if it's only from one party. And you look at TIA, IEC, IEEE, it's always a collaborative work. And it takes time. Another challenge is that it takes time to achieve consensus and have everybody being non-biased, being very professional, and agreeing on the requirements in the standard document. And for example, a standard document could easily take 2 years to develop. And it continues to change as it goes on.
Excellent.
So
Thank you. Oh.
Yep. Please go ahead.
Well, well, diving into, thank you for the explanation, and I think it's fascinating, all the effort and the coordination that has to go into it, because obviously you have to take into account all these different factors. So diving into your article, let me start by sharing the screen, because I think it describes perfectly what we're talking about and why you chose the title. I think that will help our audience understand. It's called From a Dog's Dinner to a Three-Course Meal. So please, to start, describe why the title.
Okay, so a dog's dinner is very British. It comes from my early career in research in the UK, and I worked in a university environment. Of course, it is to get things done, and then it was early years in 1999. That was when I started my first research job in the UK, and when I got into the lab. I had a senior, someone who was helping me with getting accustomed to a lab, a person by the name Ken. And I said, oh, is this how we work? This is how our lab will always look like, with all the fibers running everywhere, and we don't know which one connects to which. And this itself is only a small lab. We have a few servers, we have a few equipments and so on. And he gave the expression, oh, it's normal, it's a dog's dinner. So dogs, unfortunately, are given a lot of, in olden days, dogs are given leftovers. So this is kind of the leftover, everything piled together, and good luck kind of thing. And as I move into industry and get into Telecom Malaysia and work with different standard bodies, and we come to realize that, hey, there is actually a structure to lay your cables, to label your cables, to design the lengths and where to put the equipment. Hence, it is more structured. And that is why I took Ken's older phrase of the dog's dinner and said, now we have a three-course dinner, three-course meal. It's coming from a world of trying to share from an unstructured to a structured environment in a very basic, even laying a cable can help the industry and the operators increase their efficiency and make their network more reliable.
Perfect. And I think that's hence the name for a structured cable system, right? That with proper order, proper structure, and that will take me to the next point. If you could help us describe the elements, the key elements of what is a properly designed structured cable system.
Well, structured cable system by any forms of engineering, the first step is that it has to be able to deliver a predictable performance. A system can be very well designed, very aesthetically beautiful. If it does not work, it doesn't mean anything. So the first step of any structured cabling design is that it has to deliver the performance that your customer or the operator requires. If I need 0.5 dB loss in this section, there's this, or I need a total link loss of 3 dB, you need to design that in. That is always the first thing that you do. And of course, you need to have other than performance, it has to be flexible. It always changes. Networks always change. You have to bear in mind, because a network is not something you design in and you only work for 6 months. No, a network is something you design is going to work for 5 years, 10 years, and some networks I've seen has worked for 20 years. So it has to be able to change. Servers get taken out, being replaced with new ones, switches being replaced or aggregated, and so on. That's definitely the first step. The second step we call system availability. It really means reliability. You can perform, but if your network keeps breaking down, if I design a network, it performs great on day one, fantastic. 7 days later, it starts breaking down. A bad connector, a fiber breaking because it was not properly quality control system, or even a transceiver being operating for less than a week, and then the laser starts burning out. It happens, but we try to minimize it by following certain reliability standards in our industry. And those standards are the ones that say, when you buy something that complies to this standard, it will give you that reliability. And third is, in case of any failure, we must be ready to look into an alternative or a backup system. And when we call this term redundancy, a network must always have redundancy, especially critical networks. Telecom networks, phone networks are always very critical. They always have a redundancy. For example, in most household emergency calls, like in the US 911, it is a requirement that your phone must always work, even though there's no electricity in your home. So in the olden days, the telephone, the ports are powered from the exchange. In data center environments, if you have one server down, it has to be able to back up, go to the backup server and get all the information. So redundancy comes into mind, saying that the worst case scenario. Because remember, lives may depend. Your server may have information about a person's medical record if the person goes to the hospital, or traffic. It controls a traffic system in an intersection. So it has to be able to deliver what it's supposed to, even the main one kind of fails. And of course, the fourth one is called future proofing. Again, or another word we call it scalability. It has to be something designed for the long run. And here's where a lot of designers don't like to use the word cost effective or cheap. We always look into the total cost of ownership. So we look into the cost of ownership of a network within 20 years. We may be a higher CAPEX, capital investment in the initial, but you save on the operational expenditure moving forward. You don't need to rip it up after 5 years, put it in, that's one. If we keep failing, you don't need to send a person to go and fix it. Or even if it fails, you aren't able to deliver the service to a bank, for example, you get penalties. So when a designer design as simple as a structured cabling network in a data center or in outside plant, these are the four things. You have to be able to perform, you have to be reliable, you have to be able to anticipate failures, so you have redundancy, and of course, you want to go for the long run. You are there for 20 years, maybe, or even longer, and not 1 or 2 years. And that is the mindset of how structured cabling should be.
Perfect. And actually, that will take us into the next subject, and it goes about the older data infrastructure architecture versus the new leaf and spine. So let me share my screen again, so you can guide us through this new way of building the architectures. There. Please go ahead.
Okay, so the leaf and spine architecture is the concept of this interconnects that you see from the leaf to the spine here, the leaf switches and the spine switches. This is called mesh network. It was a idea that was used in telecom a long time ago, how to interconnect different cities and so on. Now the concept has been used for the data center network. Traditionally, what happened is that you have a fat tree or a tree network. You have the servers at the bottom, and then what you have up there is the H switch, the ones that connect all the servers. And then from the H switch, you go up one layer and you call the aggregation switch. Okay, so the H connects to the aggregation, and the aggregation switches connect to the core switch. And everything, if you have one server who needs to transfer information to another server on a different location, he has to go H, aggregation core, and come down again to aggregation H and server. So there's a path that goes through. It is well suited for the pre-cloud application world, because most data centers are storage, data storage. They don't need to process a lot of information. Information is usually stored and then sent out to a specific user, is processed there and then come back. So it's efficient, is what it is. But as we move to the cloud environment, a lot of our operating system, our applications are being processed in the data center. For example, if I were to switch on if I fly to a country, for example, the US, the first thing I do is that I switch on my phone, okay? And I get my GPS location. What it does is the phone communicates with the 5G tower or 4G tower. It goes to the data center where I am connected to, which is my cell operator. And I say, I want to know what is the weather report, or what's the transportation from here. Ask Google, what is the transportation here to my destination? What it does is that all this information and request goes to the data center, is processed, air there, and then come back. Now, imagine if you use the tree mechanism. The problem here is that the route that goes up and down takes too long. You have to wait, phone gets processed. Weather reports are fine, but if you have a GPS and direction, that you may have missed an intersection before it comes back to you. Okay, so the leaf and spine allows the data to be transferred between the servers and processed and get back to you in a faster manner. Imagine now if I have a information I need from the furthest left to the furthest right. You just need to go up to the leaf, the spine, and then come into the leaf and then the server. The path is shorter, so you increases the speed of how the data is moved within the data center. And this is what we call latency. We reduce the latency of information flow within the data center. And it's very crucial in a cloud environment where a lot of the information and data transfer happens within the data center itself.
Perfect.
And that is the key difference.
Yes. So basically, you make direct connections much easier and faster.
Exactly. Let's just say it's a shortcut.
Perfect. And then moving on to the next slide. Let me see if there. When you discuss a little bit about the dual engine and then the benefits of such, please elaborate a little bit.
Sure. So if you remember the slide before this one, we have the servers connected to the switches. Now the switches right now works very fast, 25 terabits, and now we are looking at 50 terabits coming in very soon. But the servers do not work at that speed. And the key difference that there is a difference in the speed of data being received and transmitted. So the cost of a data center or a system like this very much depends on the transceivers. I will not pay for a 400 gigabit transceiver or 200 gigabit transceiver for my server because it's expensive. and I don't need it. My server is capable to work at 100 gig, but my switch needs something faster. What do? I put 2 transceivers from 2 different servers into 1 switch pod. I reduce the number of transceivers I need on a switch. I can use a lower speed transceiver in the servers. And at the same time, I reduce the amount of power consumption. The faster the transceiver, the more power it consumes. So the advantage here is that now I am able to use the most cost-effective, or with the total cost of ownership for the next 5 years, the most cost-effective method to deliver the connectivity between the server and the switch. And the other key here is that now I also save space on the switches. I have 1 transceiver that serves 2 servers. Previously, in older systems, you have 1 server, 1 transceiver on the switch to 1 server. Now I reduce that footprint on the racking. I use less rack space, I use less power, hence I need less cooling in my data center. So that is the key advantage of the whole dual system, or even now they have the quad engine transceivers as well. There's 1 by 4 by 100 to individually 100 base transceivers.
Perfect. And that will take us to this image that I think describes perfectly the mesh topology with the breakout and a transceiver, right? And how that helps the redundancy, right?
Agree. And you are spot on, Jose. It helps the redundancy. It gives you that leaf and spine mesh connectivity to reduce the latency as well. And the new category of connectors, which is called the very small form factor, the VSFF. And you'll see a bit later, SENKO has a VSFF connector called the SN. And what happened here is that you have 4 connectors individually detachable from the transceiver, and then it can be individually routed to other transceivers in this mesh network. Hence, you'll be able to do both quad engine and also at the same time a mesh network for your leaf and spine without the need of more connections in between. So the more connections we have, the higher the loss, which is it is definitely something you want to avoid, more losses, but sometimes inevitable. But this one gives you a direct connection in the best case scenario.
Excellent. And that will take us to the next slide. Here we show the reduction of basically reducing the components, so you reduce the number of connections, right?
Yes, that's correct. So again, if you look at the standards, coming back to the standards again, the connections from the transceiver in the server to the switches has kind of a maximum insertion loss. And as the speed goes higher, the insertion loss has to be lower. Again, this is physics. It's all based on the transmission quality that you want to receive from the other side. So the LC MPO cassette, MPO jumper system has been there for a long time. It worked well. It works well. But as we go on to the higher bit rates, the higher performance requirement, you want to reduce that. We want to reduce the amount of insertion loss, and of course, for operators, you want to reduce the cost. So what do? We kind of simplified the design. This is a simplified design where you have the connector that goes from the server to an adapter, and then another connector from adapter to adapter, and adapter to the switch. The image above, you have 1, 2, 3, 4, 5, 6 connection. At the bottom one, you only have 4. So 1, 2, 3, 4, 5, 6, 7. Sorry, the above one has 7 connections. The one below only has 1, 2, 3, 4. Yeah. So that reduces the amount of insertion loss. You have less connections, less cleaning in case something goes wrong. It's more flexible. You can have a simple patch code without adding more components. And also at the same time, it in a way reduces the cost of the link itself. And if you look at a huge cloud data center, those are millions of connections in there, and it does help with all this.
So the footprint is significantly affected by reducing those components, those connections.
Exactly. You're right, Jose. By having this compact VSFF, very small form factor connectors, you can reduce the footprint in most cases at least half.
Wow.
At least half. So if you have a building, you don't want to build extension, you don't want to increase the cooling system, this is the right path to move forward. And it is scalable, it is future-proof for the next 20 years.
Great.
So you're thinking of upgrading or building a new data center, definitely this VSFF connections should be considered.
Excellent. Before I forget, in this video, in the description, we will put the link to the article. It's both in English and Spanish. So anybody who speaks English or Spanish can read it. I invite you to do so. I think you will like it. And we're coming to a close. Basically, we have here an image of this high-density connectors, in which, again, SENKO has been a leader in developing this highly compacted connectors. So tell us a little bit about them, please.
Okay, interesting. This is also called the SNMT connector, and it uses the same footprint of the SN, very small form factor connectors. It is approximately 2.5 times smaller than an MPO. So if you have a panel of MPO right now and you need to increase the density, you just change the connectors from MPO to this, you have at least double the density moving ahead. And the SNMT itself uses a newer technology, which is called a 200 micron with fiber. So the fibers right now has 9 micron core, 125 micron cladding, and a coating which is usually 215 micron. Here we use the 200 micron. There's a version that uses 200 micron, which reduces the cladding. This is IEC standard. It's been there for approximately 10 years, and you use smaller cables. The advantage of this is that if you see all the ductings and all the cable trays above the data center, the yellow ones or the ones underneath the raised floors on the data center, this will save a lot of space and the weight. So your structure will definitely be able to hold on. And of course, the smaller size allows better airflow. So your cooling system will not get blocked by bigger cables. Excellent. So these are the few things that SMT hope to enhance the design work of the data center designers.
And typically for these applications with 200 micron, I believe now mostly the uses of G657 fibers, right? Bending sensitive fibers to be able to reach such compact modules. You
are right. So the 657A and B, or A being compatible with the older 652D, and B are kind of lower band. Most of it, I guess, moving at least will be 657A. Tighter spaces, smaller cables allows you to bend the fiber more. And the 657A is a staple right now. Everybody makes it. It is quite cost effective and is available easily. So all this fibers, the new technology of fibers, smaller cores, really helps. And it gives the new tool to all the data center designers, saying that now I can design a data center with new technology, new innovation that my client could use for the next 20 years.
Perfect. Well, as we come to a close, I would like to invite you to tell our audience give one final thought or one final suggestion that might help them as they plan their data center networks.
Well, data center networks are evolving. is evolving, and there's a lot of innovative ideas and so on. And the key thing, being an engineer and also a researcher, question your design, question your traditional thoughts, and say, what can I do to improve my design and make it better for the client? And in our case, in my philosophy of network design, is simplified networking. So my brain, S, and simplified networking. Because the simpler network you have, easy to upgrade, it performs better, and it is able to be scaled up easily. And of course, the total cost of ownership will be less. So always think SN, simplified networking.
Excellent. I like that. And well, friends, thank you so much for joining us. And if you have any questions or comments or suggestions for new content, questions for the experts, feel free to leave your questions or comments in the comment section below. And we hope that this information is useful, and we see you soon. Thank you, Bernard, and hope to talk to you soon.
Thank you, Jose. It's been a pleasure. Thank you.